Welcome to week 2 of Physics 1020. This week we're going to be talking about forces and dynamics of motion. The notion of dynamics and forces is central to the understanding of motion in classical mechanics, the mechanics that we use to understand everything that is happening around us at the human scale, at the scale of planes and planets and so on and so forth. The notion of force was intuitively familiar with people dating back to the antiquity and perhaps before. But it really began to be understood with the works of Galileo in Italy, and much later really was formalized with the work of Isaac Newton, pictured here on the right, who really formulated the notion of force and the notion of how forces are changing motion, the state of motion, and how dynamics works. Isaac Newton is really the first one to have understood and discovered that. Whether it's a discovery or an invention is always unclear. But Newton is the first one to have done that. And because of that, he is often regarded as the greatest physicist of all times. What that means exactly is never entirely clear. Anyway, the central concept of this week is the notion of force. A force is a push or pull action on an object, a body. The application of a force on a body usually causes some distortion of the object or the body, or it changes its velocity, or both. Force is a vector. It's a vector quantity. Distortion caused by force. Here on the right, you have a very good example of what happens when a force is applied onto an object. So here you have a tennis racket imparting or hitting a tennis ball. And you can see that the racket itself, the net of the racket, is a little bent backward, whereas the ball itself is really squeezed and squished into almost half a sphere. So when you apply a force onto an object, the object may be distorted, may be deformed. Another example is what you would experience when you sit on the couch or you sit on a sofa or a cushion. As you sit on it, the cushion is most likely very, very much squeezed, and the amount of squeezed might depend on how you sit on it, the type of cushion you're dealing with, or how heavy you are. So sometimes distinguishing or identifying or seeing the distortion caused by a force onto an object is very easy. It's easy with a cushion, but sometimes you need a little help. So the picture on the right here was taken with a high-speed camera, and it's only this deformation of the tennis ball is lasting for a very, very short amount of time, and it's with the naked eye, so to speak, it's very hard to see it. However, it becomes quite obvious with a high-speed photograph. Now, forces will impart not only distortion or deformation of objects, but they will also impart acceleration. And this is the main topic of this lecture. But before we get to the relation between force and acceleration, let's discuss a bit how we measure the magnitude of forces. Forces can be measured in a number of ways, and you are likely already familiar with a method based on scales. So if you go shopping, let's say at the grocery store, and you buy some fruits, some vegetables, or whatever you may want to know how much you're going to pay for the goods you buy. And so you weigh them first, and then you evaluate how much of those fruits or vegetables or whatever you have in your hand, and how approximately how you're going to pay for this, how much you're going to pay for this. So the way these scales work at the grocery store is based on a spring. And so you hang, so you have a basket, you put the fruits in the basket, and the weight of the fruits pulls on a spring, and the spring then gets elongated, deformed, and the measurement of how much this spring is elongated gives us a measure of the weight of whatever you put in this basket. The greater the weight of the object that you put in the basket, the more the spring is stretched or compressed. I mean, some system can actually work in compression rather than in expansion. So the amount of stretch or compression is proportional to the weight of the object, which is driven by the pull of gravity, the pull of Earth on the object, something we'll come back to later in this lecture. And in turn, the amount of weight of an object is proportional to its mass. So when you weigh an object, you actually determine its weight, literally, and then this weight is proportional to the amount of stuff in the object, that is its mass. So you pay for the mass, not for the weight. You need a force. Forces are measured in Newton, obviously, to honor the memory of Isaac Newton. A force is considered a derived quantity. It's not a primary quantity in the sense that positions or distances and time are. But because it is so important as a derived quantity, it is given its own unit, and this unit is the Newton. The abbreviation for the Newton is N, capital N, and 1 Newton equals 1 kilogram times meter per square second. So again, 1 Newton is 1 kilogram meter per square second. So, which means that a force of 1 Newton applied to an object that would have a mass of 1 kilogram would accelerate this object at 1 meter per square second. Again, here, there's always the possibility of using the English system of unit, and so then it becomes important to be able to convert between SI system and English system of units. So 1 Newton, 1 N, equals 0.225 pounds, and 1 pound equals 4.45 Newton. This means that a force of 150 pounds is equal to a force of 668 Newton. So the next concept to really discuss and pay attention to is the notion of weight, or gravitational weight. Weight is not a measure of mass. It is not a measure of mass. It is a measure of force. That is the force of gravity applied onto an object at ground level by the Earth. So the Earth exerts a gravitational force on all objects that surround it or are on its surface, and it has a certain magnitude, and this magnitude then gives the weight to all objects that surround the Earth or are on its surface. The symbol for the weight is capital W. Strictly speaking, the unit of weight is the Newton, or the English unit equivalent. But when we ask someone how much do you weigh, they don't answer in Newton. They usually answer in kilograms or pounds. And that is because the scales that we use, the devices that we use to measure weight, are calibrated. They are designed to report not the weight, but the mass of objects. So there's a relation, there's a simple relation that we'll discuss between weight and mass. And so when we use a scale at the surface of Earth, this scale is designed and it's calibrated to give us a value in kilograms. So it measures a force, the scale measures a force, but that force, the value of this force, is immediately translated or converted into either kilograms or pounds. It is important to distinguish that weight is a force, not a mass. But when we use a scale, the weight that is measured by the scale is converted into a mass. Weight is a force, mass is a measure of inertia. Very different concepts. All right, let's get back to force, the notion of forces. Most of what we do in our daily lives, most of our daily activities involves use of forces of some kind, of some form. If you're opening a drawer on your dresser or pushing it closed, you are exerting a force on the drawer. If you are lifting a book from the table or from the floor, you are exerting, your hand, your body is exerting a force on the book or whatever object you might be lifting. If you throw a ball or a football or a baseball or whatever you throw, your arm are exerting a force on the ball which will accelerate the ball, and as you let it go, it will just then travel some distance. The action of walking, running, involves the forces that are developed or expressed in your legs by the muscles of your legs. There is the contraction and relaxation of the muscles of your legs means that you can move your legs back and forth, and because you are standing on the ground, the contact point between your feet or your shoes with the ground exerts a force on the ground. So you exert a force on the ground, and as we will see in a moment, the ground reacts by pulling, effectively by pulling your body. So as you move your legs, you end up moving forward or backward or sideways, and so on. Now, the notion of force, or the understanding of force, has evolved quite a bit since the antiquity. It's no secret that some philosophers of the antiquity, like Socrates, Plato, Aristotle, were very, very clever, very smart, and very learned people. And Aristotle in particular spent quite a bit of time trying to study the laws of nature, or trying to understand nature. And he came up with some ideas as to what motion is and what forces are. It turns out that Aristotle, though arguably a genius, got it a little bit wrong. Actually, he got it quite wrong. And that's because he did not account for something that we now know and understand very well, the notion of friction. So friction is essentially a force. It's a resistance that opposes the relative motion between two objects, two bodies, or substances in physical contact. If you're sliding your foot on the ground, you're sliding your hand on the desk, you're rubbing your hands together like so. You feel this friction. You feel, even if you did this for a while, you would feel that your hands are warming up. And that's because some energy, a concept that we'll talk about, some energy of motion is converted into heat. And so the friction is absolutely important for us to function in the world. Without friction, we would not be able to walk. Without friction, the tires of our cars would not have any traction on the roads, and we would not be able to drive, not in the way that we do anyway. So friction, as it happens, is something that originates from the contact point between two surfaces, or something at the boundary of materials. And so exemplified here are two objects, one depicted in somewhat of a green color, the other in gray. And you can see that the surfaces, although if you were to look at them on a macroscopic scale, so if you look at your desk, for instance, you could think that the desk is smooth and flat, right? However, if you were to look closely, you would realize that there's all kinds of non-uniformity in the surface of the desk or any other surface. And as you put two objects in contact, these non-uniformities basically resist the relative motion of the two surfaces. So because of these different asperities, these different deformations, small deformation, and because of electric forces at these surfaces, as you try to slide the two surfaces relative to one another, there's resistance because of this structure, these different bumps so that then opposes the relative motion, the sliding of the two surfaces. This sliding becomes even more difficult to achieve when the two surfaces are really tightly bound to one another, or tightly, not necessarily bound, but pushed against one another. And so if the two surfaces are loosely in contact, then the sliding is easy. When you push them really strongly against one another, then the sliding can become very, very difficult. And so we say that the amount of friction, it depends on the force the two objects apply onto one another. This force is usually called the normal force or the contact force. Now, such forces are all around us. So imagine that you are going to a city like San Francisco, for instance. San Francisco is a beautiful place, but it's very hilly. So if you park your vehicle, you are very likely to end up parking in a slanted road, such as depicted here. And so when you park, you hope that your car is not going to slide, right? So you hope that there is enough traction between the tires of your car in the road. And so then the car stays at rest in a zero motion, no velocity, no motion relative to the road. This is a case of static friction. The friction is applied in between objects that are not in relative motion. We say that it is static because there is no motion. However, there's also the case of kinetic friction, and this is depicted on the right with a car trying to negotiate a curve at somewhat high speed. And you can see from the image that the driver, probably a very skilled driver, but nonetheless has lost a little bit of the control here, and the car is skidding to the left. And so the tires, particularly the back tires, are no longer just rolling on the road, they are sliding to the left. And so that means that the point of contact between the tires and the road is not static, but it is sliding. So we speak of kinetic friction. That's an example here for a car on a road skidding through a curve. It's also the case of an aircraft moving through air. An aircraft is surrounded by air. As the aircraft moves forward, air is flowing through or around, I should say not through, but around the aircraft. But at the point of contact, there's a bit of a friction between the air itself and the plane, and this causes a resistance against the plane being in motion. Likewise, if a fish is swimming underwater, it has to push the water, and as it pushes the water to move forward or backward or what have you, the water must slide on the body of the fish, and that also imparts some resistance towards the motion of the fish. So this is the context in which Newton formulated his three laws of motion. Newton's formulated three laws of motion, which are known as the first, the second, and the third. A little boring, right? So the first law is the so-called inertia law. It states that an object will remain at rest or in uniform motion with constant velocity unless acted on by a net external force. If you go back to the days of Aristotle would say the natural state of motion of an object is to be at rest. What Aristotle did not understand was that friction is a force. And so if you have an object in motion, friction is omnipresent. It's always there, and it will tend to drag the object to rest. And so that is something that both Galileo and Newton realized much later, indeed, several centuries later. And so Newton was able to then recognize that an object would remain at rest, which is what Aristotle would have said, but Newton also said the object would actually remain in motion, in linear motion, so long as no external force is acting on the object. An external force could be perhaps gravity, but it also could be friction, some form of force of friction. That's the first law. The second law, which we will expand on quite a bit in a few moments, is the relation between force and acceleration, the so-called F equal ma law. The third law is a little more subtle, but nonetheless very important. It's the so-called action equal reaction law. So let's expand on each of these a bit. The first law. As I said, Aristotle had figured out that the natural state of an object is to be at rest. And that's because he didn't really understand the notion of force. He didn't really understand that there is such a thing as friction, which tends to basically drag object to rest. Galileo was the first, conceivably, or arguably, to realize the importance of friction, and he found out that if objects are sliding on smooth surface or smoother surfaces, they tend to slide longer and further. This is something that you can experience or you can observe if you're a hockey fan. So go outside, take a hockey stick, a puck, and go on the concrete or the asphalt of your driveway, and then hit the puck. Well, obviously the puck will slide for a while, but probably not very far. Well, it depends how hard you hit it, of course. Now imagine doing the same thing at your favorite ice skating rink, or at your favorite arena. So, or just picture a game between the Red Wings and some other team. As they hit the puck on the ice, you can tell that because the puck is sliding on the ice, and the ice is slightly warm on its surface, there's very little friction between the puck and the ice, so the puck can actually go across all the way across the ice without without stopping or without slowing down all that much. So Galileo understood this, although Aristotle did not. So 1 point for Galileo, and many points more for Newton. The way you can understand this is through this experiment that Galileo did. So take an object depicted here by this ball here, and let it roll down this incline. As the ball rolls down, it will then continue to roll on the horizontal side, and then eventually what you find is that it tends to come back up. What you find is that if there is no friction whatsoever, the ball will come back at the same height. What Galileo observed was that if he changed the incline of the second edge, you would see that the ball would actually go further out. It would keep rolling further out. So essentially what Galileo did here is that he effectively decreased the force on the ball that was slowing down the ball. And then he was able to observe that the ball rolls further. Now, if you take this incline and you make it completely flat, then you find that the ball will roll down the first edge, and then it will keep rolling without slowing down all that much if there is no other incline on the right hand side. So effectively, what Galileo understood is that if there is no opposition, no force acting against the ball will keep rolling for a long time. And so effectively Galileo understood that if you don't apply a opposing force or a force of friction, the ball would roll forever. And this is eventually what led to Newton's formulation of the first law. If one person pushes on the front of your car while another pushes on the back with equal effort, if the two forces are equal, effectively there's no net force. So if the vehicle is at rest, it will remain at rest. If the vehicle is sliding or rolling, then the vehicle would effectively keep sliding. Imagine that if you're trying to push a very large truck, no matter how hard you try, your shoes will not have enough friction on the ground, or your arm muscle will not have enough strength to push, to stop the truck. So if the force is imparted by these two gentlemen here, if this force is really negligible relative to the size of the truck would just pass through, right? And so effectively friction is something that would slow down the truck, but the amount of friction is also something that matters relative to the size or the mass of the truck. So if if you want to stop the truck by exerting a force against the truck, you would need to have a sizable force. In this example here, the two gentlemen are pushing in opposite directions. So effectively, the two forces they exert cancel one another. So effectively, it's as if there was no force on the truck. Of course, that sounds a little silly to do this. You could say, well, okay, the truck is stuck in the ditch, you know, slid off the road in the winter. Now it's stuck in the snow and you want to push it out back on the road. And so the two guys go at the back and they exert the same force, but now in the same direction. Now you have a bit of a chance to get the truck moving. Although if the truck is very big, good luck. You know, no matter how strong these two guys are, it will be hard to move the truck because of its size, the amount of stuff it contains, because of its inertia. Let's expand on this notion of uniform motion, right? An object will remain stationary unless a net force causes it to move. That's the first part of the first law. The second part is an object in uniform motion will remain in uniform motion, that is in a straight line, unless a net force causes it to change speed or direction. This is the archetype here of this situation where you have a ball attached to a string and somebody's holding the string and spinning the ball around their hand, like as illustrated, right? What you find is that if you're not spinning, the string itself might be loose, right? The minute you start spinning the ball around your hand or your head, as the case may be, you observe that the string suddenly becomes taut, right? It becomes as elongated as it can be, and you can see that it is tense. There's tension in the string. And it is this tension that will bring about the ball to spin around in a circle as illustrated here. The more force you exert on the ball, the faster you will manage to get the ball spinning in circle. So there's a relation between the tension in the string, the force exerted on the ball, and the velocity imparted to the ball. The bigger idea here is that as you apply a tension on the string, you apply a force on the ball, and this force makes the ball go in a circle. Imagine now that you are applying so much tension on the string that it snaps. Imagine that you're using a very flimsy string and the string snaps somewhere along its length. When that happens, what you will observe is that the ball will not be any longer pulled by the string, and it will continue its merry way on a straight line, as illustrated here. So whatever velocity it has at that point when the string breaks, the ball will keep. It will keep the same speed and it will keep the same direction. So with no force imparted on the ball will keep going along in uniform motion, which means constant speed and same direction. And that is the true meaning of the first law. It's not only the speed that can change, but it's also the direction. And to achieve that, you need a net external force. Let's now discuss the second law. What the second law tells us is that there's a relation between the magnitude of the force and the magnitude of the acceleration. So let's take this guy here. imparting a force on his car and trying to move his car. The same guy now could next go to the grocery store and go shopping, and then this guy now could push a cart. So let's play this exercise that the guy is pushing with the maximum force he can exert on the car. And let's pretend that he exerts the same magnitude, the same maximum force on the cart. It stands to reason that as this person does this, the cart will start moving along much faster than the car will. And that's because the cart is small. The cart doesn't likely contain all that much. So the inertia, the mass of the cart is much smaller than the inertia or mass of the car. Consequently, the same force will lead to two different acceleration, two magnitudes of acceleration for the car and the cart. And the relation between the force and the mass is indeed, the relation between the force and the acceleration is indeed the mass. Mass is the property of matter that makes it resist acceleration. It's what we call inertia, something we've already spoke about and we'll speak about some more. A car is large. It has a lot, it's made of metal, it's made of all kinds of things, and it has a lot of stuff, right? So a car is in general more massive than a cart. So it has more inertia. And as such, applying a force onto the car will not cause the same acceleration as applying the same magnitude of force onto the cart. And so the cart would accelerate quite fast, but the car will not. And so mass is what constitutes the proportionality between acceleration and force. So mass is really a measure of an object's resistance to acceleration. It's a measure of its inertia. The amount of inertia of an object, as it turns out, depends on how much matter is composing the object. What it means in practice is how much stuff it composes the object. Is it made of wood? Is it made of plastic? Is it made of steel? Is it made of gold? Is it made of... So whatever material constitutes the object determines how much matter is in this object. And this amount of matter is what determines the inertia of that object. So quantitatively then, we can get to the second law, the expression of the second law shown here. The second law is, it turns out, the most important tool for applying mechanics in the real world. If you want to accelerate an object, you need to apply a net external force on that object. The magnitude of this force, the magnitude of the net force, will cause an acceleration which depends on the mass of the object according to this equation. Force equal mass times acceleration. Note that both F, the force, and A, the acceleration, are adorned with an arrow, which means that both F and A are vectors, while M is a scalar. So M being a scalar, it doesn't have a direction, it just has a magnitude. So F equal ma means that the force will always be in the same direction as the acceleration, and conversely, the acceleration will be in the direction of the force. Now let's be clear. Velocity and acceleration are not always in the same direction. We've seen this already in week 1. So acceleration and velocity can, but don't have to be in the same direction. Sometimes they are, sometimes they're not. If I go back to the circle here, you can see that the velocity of the ball is along the circle, whereas the force is along the string connecting the ball to the hand. So the acceleration is along the string. So the force and the acceleration are in the same direction. The acceleration is in a very, very different orientation than the velocity. Something to remember. Right? So the force is always in the same direction as the acceleration, but the acceleration or the force are not necessarily in the same direction as the velocity. That can be a little confusing at first, but if you think about it, it makes sense. Now let's get back to the connection between mass and weight. Mass and weight are very, very different notions. One is a measure of inertia, one is a measure of force. Right? So mass is the measure of inertia of an object, the amount of stuff in the object. It's an intrinsic property of the matter composing the object, whether it's gold, lead, wood, plastic, air, what have you. Whereas weight is a measure of the force of gravity of Earth onto an object. So weight is a force that arises from the gravitational interaction of the Earth with an object. However, as it happens, the weight of an object is proportional to its mass. And this is something that Galileo already had some inkling or some concept of, but this was better formulated and more clearly formulated with, or by, I should say, Isaac Newton. So the relation between weight and mass is shown here. Weight, W, equals mg, where g now is also a vector and is known as the gravitational acceleration at the surface of Earth. It should be clear that g, the acceleration, is a vector, and it has a magnitude that is specific to the location on Earth. If you are right at the surface, right at sea level, it has a magnitude of 9.8 meter per square second. If you go to higher altitude, then g is different. It is smaller. If you go on the moon, if you go on Mars or other planet, the value of g on the surface of these planets, bodies, is different. Again, here we have a vector relation. W, the weight, the force exerted by the pull of Earth on an object of mass m, is along this gravitational acceleration. So to put this in calculation, and this is something you'll do quite a bit in the next week or so, we have to remind ourselves that the unit of force, or the unit of weight, is the Newton, and it's defined as such. 1 Newton equals 1 kilogram times 1 meter per square second. A mass of 1 kilogram then, near the surface of Earth, weighs 9.8 Newton. So 1 kilogram times 9.8 meter per square second, which is g, the value of g, gives us 9.8 Newton. On the surface of the moon is a smaller object. It's a smaller body, and it has a smaller pull of gravity. And one finds that at the surface of the moon, the value of the gravitational acceleration, the value of g, is 1.6 meter per square second. So if you have a weight of 1 kilogram, the weight of 1 kilogram, the weight of an object of mass 1 kilogram is then On the moon, 1 kilogram times 1.6 meter per square second. So that's 1.6 Newton. So you see that an object of 1 kilogram would weigh different things on Earth and on the moon. On Earth, it has a weight of 9.8 Newton. On the moon, it has a weight of 1.6 Newton. If you bring this object now to Mars or Mercury or Venus, it will have also different weights on these planets. So the relation on Earth depends on the gravity, the gravitational acceleration of Earth, which on the surface happens to be 9.8. So the weight is m times 9.8, where m is in kilogram and w, the weight, is in Newton. Okay, let's take an object of 2 kilogram, a brick of 2 kilogram. Its weight is 2 kilograms times 9.8 meter per square second. That's essentially 19.6 Newton. This same brick on the moon would be subjected to a gravitational acceleration of 1.6 meter per square second. That means on the moon, it would have a weight of m times 1.6, 2 times 1.6. You do the math. You can obviously convert in pounds. I will let you read this. You can consider examples just to familiarize yourself. How much would a 700 kilogram car accelerate if I exert a net force of 140 newtons on it? And then you can ask yourself, how long would it take to speed up to 10 meters per second, which is 22 miles per hour or 36 kilometers per hour, if the same force continues to be applied? I'll let you think about it for a few seconds. Well, we know that F equals ma, which means now I can rearrange the equation and say A equals F divided by m. I gave you the magnitude of the force. It's 140 Newton. And I gave you the magnitude or the size of the mass, 700 kilogram. So the acceleration is 140 Newton divided by 700 kilogram. That is 0.2 meter per square second. Now, if the object starts from rest, velocity of 0, then its velocity at constant acceleration of 0.2 meter per square second would increase. Its speed would increase in relationship to the time applied, the force is applied, right? So V equals the magnitude of the acceleration times t. So if you want to achieve a certain velocity, let's say 10 meters per second, then you need to apply this constant acceleration for a certain amount of time. So V equals AT means T equals V over A. So the time then is the speed you wish to achieve, 10 meters per second, divided by 0.2 meter per square second, which is the acceleration we just derived. And 10 over 0.2 is obviously 50 seconds. Next, I can ask myself, how far will the car travel in this time if it starts from rest? I give you here a few other options, and I give you a few seconds to think about it. What we saw, if you recall, last week is that the distance traveled at constant acceleration, if you start from rest, would be equal to 1/2 the acceleration, the constant acceleration, A, times the square of the time elapsed. And so now we have that D is 1/2, the acceleration is 0.2 meter per square second, and we just calculated a time of 50 seconds to reach the velocity that we wanted. And so you then 1/2 times 0.2 is 1 half times 0.2 is 0.1. The square of 50 is 2,500, and so 0.1 times that is 250 meter. Let's consider another example. A car manufacturer decides to build a car that can be accelerated uniformly from 0 to 60 miles per hour in 10 seconds. Okay, that's not particularly impressive, but let's consider this as the example. In metric units, this means that the car would go from 0 to 27 meter per second. Right? It's 0 to 27 meter per second, and the car will achieve this in 10 seconds. And now we'll pretend that the car has a mass of 1,000 kilograms, just to keep it simple. And so what amount of force is required to achieve this? What amount of force is required to accelerate the car from a zero speed, v equals 0, to a speed of 27 meter per second? Again, I'll let you think about it for a few seconds. So as we just saw, the relation between acceleration and velocity and time is written here. So A equals V over T, which means that if we want to achieve 27 meter per second, and we have 10 seconds, that requires an acceleration of 2.7 meter per square second. In turn, the force will be the product of the mass times the acceleration. The mass being 1,000 kilograms multiplied by an acceleration of 2.7 will give us a requirement for a force of 2,700 Newton. And so in a little bit more of detail here is that the acceleration is the change in velocity, delta V, over the amount of time required to effect this change. So it's 27 minus 0, which is 27, divided by 10 minus 0, which is 10. So 27 over 10 is indeed 2.7, and now you plug in the 1,000 kilograms, the 2.7 acceleration, and you get indeed 2,700 newtons. Let's revisit the notion of circular motion and discuss the notion of centripetal force. A centripetal force is a force acting sideways on a moving object, and this force causes a centripetal acceleration. That is a motion that is in a circle or segment of a circle. It doesn't have to be a full circle. It just has to be the segment or part of a circle, and that means a motion with a constant radius. So the object moves along a circular path or a fraction of a circular path as long as the net force remains perpendicular to the velocity of that object. The size of this centripetal force to achieve this acceleration, to achieve this motion, F equal ma, can be shown, and we will show that in a moment, to be v squared over r. So the acceleration of an object in going at a speed v around a circle of radius r is v squared over r, and consequently the force to achieve this, the force required to achieve this, is a so-called centripetal force. That is a force directed towards the center of the circle, and this force has a magnitude of mv squared over r. So let's consider this now. For a car going at 10 meters per second around a curve with a radius of 20 meters. If the car's mass is 1,000 kilograms, we can ask ourselves, what is the centripetal force that acts on this car to achieve this circular motion? Well, the force is mv squared over r. The mass is 1,000 kilograms. The velocity, the speed rather, is 10 meters per second, which we square. That's 100 square meter per square second. We divide by the radius of curvature of the path, that's 20 meters, and we get 5,000 Newton, which you can convert into pounds if you wish. Now, the acceleration itself would be just v squared over r, so that would be 100 squared divided by 20. Turns out that's just 5 meters per second. And so we get the same result. So it takes a force, a centripetal force, to keep an object going on a curve, going on a circular path. So it means that to keep an object on this circular path requires the force to be strong enough given a velocity and given the mass of an object. So the centripetal force acting on a car going around a flat curve is supplied by the friction between the tires on the road. So here imagine that you have this car, right? This car was trying to negotiate this curve, but it seems as if the car was going a little too fast and there was not enough friction between the tires and the road. So the car started sliding, skidding, and went off-road, which can be pretty nasty if you ask me. So obviously the faster the car goes, the stronger the force will need to be to keep it negotiating a curve of equal radius. And so that means that the force of friction imparted by the tires in contact with the road, this force would have to be large enough to provide the friction that will make the car negotiate this centripetal acceleration. It stands to reason that if you try to go too fast, at some point this friction force, is no longer large enough. So the static force is no longer large enough, and the car starts sliding. And what one finds is that friction force tend to be smaller when they become kinetic as opposed to being static. And so at that point, then the friction between the tires and the road becomes smaller, and the car will tend to slide. And if you're going way, way too fast, the car will slide off-road, as shown here. The pictures at the bottom shows the same situation for a truck that was going a little too fast as it turned around this curve, and then the truck then tipped over. So we can examine this quantitatively. This is done here. You have a car going a straight segment of road, then it turns to the right, and it needs to apply some force to negotiate this curve. And so you have a curve with a fixed radius, or let's imagine it's a fixed radius. And so it means that if you now want to go twice as fast, the force would have to be 4 times larger. V squared, twice V is 4V squared, right? So you need a force that is 4 times as large. So let's do this in a quantitative example. We have a string held by this lady here, and the string has a maximum tension capacity of 10 Newton, and we're trying to spin a 1 kilogram object, which is not as easy as it sounds. And you want to spin this object at a radius of 10 meters using this string. Well, I don't think this example is quite realistic, but let's carry on anyway. So a force of 10 Newton, a radius of 10 meters. And so we can ask ourselves, what is the maximum speed that can be attained by this mass without breaking the string? So I have a few options here, and I will let you think about it for a moment. The answer is 10 meters per second. So how do we find this? Well, we have that the relation between the force and the acceleration is given here. M is the mass, v square is the velocity, the square of the velocity over the radius of curvature. I can then solve for v, so I bring r to the left, m to the denominator, and I take the square root. So I have that v equals the square root of the force times the radius divided by the mass. Plug in the numbers. Force is 10 Newton, radius is 10 meter, and the mass is 1 kilogram. There's a typo here. It should be a lowercase k. And so you have 10 times 10, that's 100, divided by 1 is 100. The square root of 100 is 10 meter per second, indeed. I'm going to stop here, and this will be the conclusion of part 1 of this lecture, and then we will reconvene in part 2 very soon.